Okay, so I will start where we left yesterday about the different methods applied for the electrical distance measurement. We have introduced the first method with the time of the flight, and the second method is the it's called the phase measurement. We introduced some of the potential issues with respect to the phase measurement. Basically, during the for the EDM, we cannot identify how many number of the total waves that we can measure from the sender to the reflect back to the receiver, but we are able to measure the phase difference from the outgoing signals and the incoming signals from the receiver. So the phase difference is the key variable that we're going to use to identify the distance from your start point to the target. And here the phase difference will define as the shift of the waves from the sending signal, from the outgoing signal to the incoming signal. And we will just represent the partial waves that we can make from the EDM machine. And to make it simple, we will list here. I listed the equations to the calculation about distance from your target from your start point to the target, which will be n times 5 times lambda divided by 2. Here, n is the number of the complete waves, but as I just explained, it cannot be counted because we don't know how many waves in between. And the 5 is the partial waves, which will be the phase difference. This is the part that we can measure. Here, lambda is the length of the wave, which can be determined based on the frequency of the signal that we send. And with this information, we will be able to identify the distance from the start target. But of course, as we don't know the value of n, so we cannot find out the accurate value of L with only one frequency. So what we do for the measurement with the for the phase measurement is like we will send out the waves with multiple frequencies. So the first thing at the very initial step, the machine will send a very long wave, a very long wavelength, and the length of the wave is long enough, which indicates that we will not observe any full waves during the measurement. So we're gonna assume that n will be 0. With that, we will have L equal to 5 times lambda divided by 2, as for the case n equal to 0. And this can give us a very give us an approximation about what's the distance from your start point to your target. So for example, let's consider an example. Say that we're going to measure the true distance about 7,468.345 meters, and the machine will send out a wave with a length of 20 kilometers, which will be much longer than the distance we want to measure. And of course, you will not observe any complete wave during this measurement. So what we find that from this first measurement, we find the phase difference as 0.75. So with that, we can estimate the length as 0.75 times the wavelength. The wavelength is 20,000 meters divided by 2, which will give you the distance of 7,500 meters. So that's the first measurement. Of course, it's not quite accurate because the accuracy is totally rely on the phase difference, and there are some resolutions about the phase meters to identify the phase difference. But that should be fine. We will have the other steps to further increase the accuracy of the distance measurement. So with the first step, we will find out the range, the potential range from your start point to the target. And then In the next step, the machine will send out a shorter wave. Say that with the wavelength of 3 kilometers, and with this one we can approximately identify how many whole waves will be observed during this whole moment. Originally we have the equation n equal to L equal to n plus phi times lambda divided by 2. So this L is the length you measured. And if you have the value of lambda equal to, which would be the wavelength as 3,000 meters, we have phi equal to, you measure phi equal to 0.98, then you can calculate the approximate number of the value of n from this measurement. So what we do about that is like first we need to find out the approximate value from the first measurement. So with the first measurement, we get the value is 7,500 meters, and in the second iteration, we have L2 equal to m plus phi times lambda divided by 2. And if we say that the L2 is approximately equal to L1, so they should be close to each other, that will be 7,500 meters. And we know that the value of phi is 0.98. The value of lambda is 3,000. And we also know the estimated distance is 7,500 meters. So with that, we can get n approximately equal to 4.02. So we can claim that in the second measurement, n will just be 4. This is an integer, as in the full number of the waves that you're going to observe. So now we will have the full number of the waves that we approximately will observe with the wavelength of 3 kilometers. And we observe the phase difference as 0.98. With that, we can calculate the value of distance measured in the second iteration as 4 plus 0.98 times 3,000 divided by 2, which will give you the value of 7,470 meters. This one is actually closer to the true distance. The true distance is 7,468 meters. So the difference is only around 22 meters compared with the it's only around 0.022 meters. So this is quite accurate compared with the previous one with the first measurement. So here, sorry, here's the ratio of the error. So the ratio is less than 0.022. And then we can do the other iterations. We will send the waves with the shorter length. We can reduce the wavelength to 500 meters, 100 meters, 50 meters, 10 meters, 2 meters, even to 0.1 meters. And with all these iterations, you can find out the number of the whole waves based on the calculation as shown in the second iteration. You can measure the phase difference, and then you can calculate the distance you're going to measure for each iteration. If you go through this step, you can eventually find that the percentage of the error will be reduced to a very small value, eventually will reach to 0. This indicates that your estimation will be very accurate. And with that, we can rely on the result from the EVM to identify the distance from your origin to your target. So this is the mechanism for us to use the phase measurement to conduct the distance measurement between 2 points with the electrical distance measurement tools. But of course, there will be some issues about the phase measurement and the time of the flight measurement. For the phase measurement, the phase shift method is usually will be more accurate compared with the time of the flight, and it will allow the very narrow beams, but it can measure but the distance it's going to measure is limited. It depends on the maximum wavelengths that the machine can send. For the time of the flight, it will has a much wider range to measure, but the disadvantage is that the accuracy would be low, especially when it's applied to measure the short distance. And this is due to the built-in clock. We cannot find out the exact durations of the time durations for the light to be sent from the time you send it to the time you receive it. And usually for most of the EDM tools, we use the phase shift or the phase measurement to measure the distance. And we can also, if we think that the measurement is not accurate enough, we can conduct the measurement for several times and use the average value to further improve the accuracy. And another issue is like usually for the phase measurement, it will take a longer time to get a result. But for the time of the flight, it's very short. You get a result immediately. But also there will be some advantages about the time of the flight method. Usually the time of the flight method will be very efficient for the long distance measurement, or for the case you want to get the result in real time. But for the short distance, it's better for us to use the phase measurement, but you need to allow some time for the machine to get an accurate result. So that will be all about the introduction of the electrical distance measurement tools. So with that, I will conclude this lecture. And do you have any questions, follow-up questions about this topic? Okay, let me see, I saw some. So I see the questions about the what's defined as the short distance. So the definition about short distance is related to the maximum wave that the machine can send. Like for the example in this lecture, we say that the distance, the maximum wavelength say is 20 kilometers. With that, you probably can only measure up to 10 kilometers, because you need to consider the trip from and back. And as the short distance is some relative terms depending on the capability of the machine, and especially for the case, for the example with 20 kilometer maximum wavelength, we have to make sure that the distance you're going to measure is less than 10 kilometers, or even shorter. With the shorter values, with a shorter range, the distance, the measurement would be more accurate. Okay, so that will be the contents about the EDM. If you don't have any additional questions, I will go to the next chapter about the topography. So just wait for a minute. Let me switch to the next note. Okay, so the topography is actually another technology that we can apply to get a better understanding about the elevation profiles along the region that you measured, especially the connections between the elevations and the locations that you measured, horizontal and the horizontal locations that you measured. In our previous lectures, we have actually introduced the elevation profile. we are going to show the elevations at different horizontal locations. Usually you're going to have a graph like x-axis will be the horizontal distance from one point from origin, and then you have the vertical distance or the elevations and their different horizontal locations. So this is about the elevation profile, and it's just a one dimension profile. It can only tell you what's the elevations along the line. And it will be very great for you to do the measurement, especially for the construction of the road or to identify the elevations of the boundaries. But when it goes to the survey about the area, about the land, then the one-dimensional description will not be enough. Instead, we will need to rely on the topographic mapping, where it will show the elevations at the 3D at a 2D dimension, and the figure on the right shows the control plot about the topographic mapping. It will show the elevations at any locations in the area, in the land or in the area. And in this figure, you will see some contour lines, and each line will represent the one elevation. So along the contour line, the elevation will be the same. So this is a very brief introduction about the topography. And now let's go to see how we can read the topography maps. Usually the topographic maps will show the elevations in the area. For example, if we want to measure elevation around the mountain, and we can transfer them to the contour plot in the 3D plane. And in this 3D plane, you will have the, several contour lines. And as I just explained, each line will represent one elevation. So at the outside, you will have the mean sea level, which will be the locations with the elevation of 0. And you will then have the elevations around 10 meters. You will know along this line, all the points will have the elevation of 10 meters. And similarly for the other contour lines, 20 meters, 30 meters, 40 meters, 50 meters. If we go to check the whole contour plot, if we find that the contour line are closer to each other, it indicates that the slope there is much steeper. But if they are far away to each other, for the especially for the region here, if they are far away to each other, it means that the slope may be small. It's a smoother compared with the region with very close contour lines. And also, sometimes you can find out a point associated with the number with the elevation. This will usually indicate the peak point in that area, which will be the local peak point or the local lowest point. It will tell you the highest elevation or the lowest elevation depending on the values you observed. So with that, you can, with the topography mapping, you are able to find out the values, the elevations at any point in the 2D area. And now the issue comes to us is how we're going to draw the topography map. Well, usually what we do is like we will try to do a survey about a lot of random points along the area. We cannot do the survey about all the points. That's impossible. What do we do is that we just select some random points. This one is quite similar to what you do for the lab 5. You will select a set of points in the area you want to measure, and you measure the elevations, and you measure the locations of that point, and we use those information to draw the topographic map. For another thing, we have to know that at each point in this 2D space, we want to transfer the elevation to the topographic map. So we want to use the point we measured, and we also want to use this point to interpret what's the other points that we haven't measured. What's the elevation of the other points in that area? so that we can have the full understanding about the topography of that region. So here would be the here will be one example about the 3D surface on the area. And in order for us to draw the topography, we have to utilize the triangulation technique, which will be commonly applied in the 3D surfacing models to complete the drawing of the topography map. And for the rest of the lecture, I'm going to show you how we're going to apply the triangulation technique to complete the drawing. So to do the triangulation for the surface property, what we need to do is like we will usually consider the using the random points that we have already collected and try to connect those points and form a lot of triangles in the 2D region. Here I'm just take one example for you to understand the triangulation. Assuming that we have measured a lot of points, which will be the dots in this graph, and then you can connect those points for any 3 points. You can form the triangle. Usually we're gonna choose these points which are closest to each other. And now, as you know that there will be a lot of points, and it will be possible for you to form multiple triangles. For example, for this point A, B, C, D, you can form 2 triangles ABD and BCD. So this would be 2 different triangles. And you can also form another type of the triangles, A, B, C, D. So you can get the triangle of ABC and the ACD. So that will be 2 different ways for you to identify the to define the triangles. But now it comes to the issue. In the triangulation technique, we assume that the elevation is changing smoothly or it's changing linearly along each line that you draw. So for example, for the first method, for the first method to identify the triangle, the elevation from the point B to point D is changing smoothly from 990 to 980. So if we go to check the midpoint of this line, then the elevation will be just the average of these 2 values. That is 985 meters. But if we use the other methods, considering the triangle with ABC and ACD, you can find out the line which will connect the point A and point C. The elevation at point A is 10, elevation at point C is 36, and if you go to check the midpoint, you will find out the elevation is 23, which will be half of the 10 plus 36. And clearly, these 2 values are very different to each other, even though they represent the same point in the 2D area. So there must be one indicator. There must be one method is wrong for you to identify the triangle. So now the issue is like how we can find out which one is right, which one is wrong for us to generate the triangles. So what we do is like we have to use the Delaunay triangulation technique. And this one will give you ideas about how to exclude the wrong method to form the triangles. So in this Delaunay triangulation method, at first we will join all the exterior points. So we will just try to draw the line to cover all the exterior points and form the parameter around all the points you measured. And then we will add one interior point once at a time and connect this interior point to all its surrounding points in the parameter. And we're going to check that whether this kind of connection will satisfy the condition of the circular condition. For example, in the Delaunay triangulation, they assume that if you have any three points to form a triangle, you should using these 3 points. You should using these 3 points to form the circle, and make sure that this circle will not cover any other points that you measured in the 2D area. So if you go to see, this would be the rule you have to apply. If you go to see the previous example, for the scenario on the figure A, if you have the triangle of ABD, you can form the circle, and you will observe that this circle will not cover any other points that as you measured in this situation. But if you use the triangle ACD, you will generate a very large circle, which will definitely cover all the other points that you measured at the bottom of this 2D region. So this indicates that the one that you determined the way for you to specify the triangle by connecting ACD and ABC will not be the right way for you to do the triangulation. You have to choose the one as shown in figure A. So that's the Delaunay triangulation, and we have to always check this method, this criterion, to make sure that the triangle that you defined are correct. So this is the basic idea for the Delaunay's triangulation, and we also have some fundamental rules for you to use. Usually for the Delaunay triangulation, we can identify how many of the triangles will be formed, and it could be easily calculated if you have n points, and there are 10 exterior points which will apply for you to form the parameter, then the total number of the triangle that can be formed would be 2 times n minus 2 minus k. So this is the number of the triangles can be formed based on the Delaunay's triangulation rule. We're gonna show you, for now I'm gonna show you the one example about how we can apply the Delaunay's triangulation. First of all, assuming that we have 7 points that we measured, we know their locations, we know their elevations. The first thing we need to do is do the triangulation. From the Delaunay's triangulation rule, what we need to do is I first need to connect all the exterior points. So this point 1, 2, 3, 4, 5. Those would be the exterior points. And this parameter should cover all the other points in the all the other points you measured. Make sure that all the other points are inside the parameter. And now that's what we do. Join all the exterior points. And the next thing we need to do is trying to connect with start with one interior point and connect that interior point to the all the points in the parameter. Say that we're gonna start with the point 6 here. What we do is like we're gonna connect the point 6 to all the points in the parameter. And then we must check that the circles formed for each triangle will not cover the other points. But at this step, we just assume that this point does not exist. Assume that this one can be removed. And double check whether the whether all the triangles will cover any other points. If it covers any other points, then it means that we cannot use this use that triangulation. So for this example, we can make a quick check, and for the triangle of 1, 1, 2, 6, you have this kind of circle, and it does not include any other points. And for 6, 2, 3, that will be this circle. And of course, it does not include any other points. You can double check the other points. It's you will find that the this kind of triangulation is totally fine. And now the next thing we need to do is add one interior point one time. So we have another point 7 that we have measured in the field, and we to add this point in the triangulation, we first need to check the parameters. So for the point 7, it includes the parameter of the point 7 would be this triangle, and then the next step is like we're gonna try to connect. We're gonna try to connect the point 7 to the other points. So that will be point 3, 4, and 6. And with that, we have 3 triangles generated, 1, 2, and 3. And now I have a question for you. Do you think this triangulation is appropriate or not? Can you see any potential issues? Does it satisfy the rules, like the circle it formed will not cover any points you measured? Do you have any ideas about it? Okay, we can start to check them one by one. First for the 3, 4, and 7, that will be straightforward. It will be very easy for you to identify. Join a circle, and this circle does not include any other points. So that's the first thing. And then for the triangle 1, you draw another circle. Well, this should be in a very large circle, and definitely it will cover the point 2. So this indicates that the triangle 1 is not an appropriate one. It may not be appropriate for you to connect 7 to 6 and 3. And similarly, you will observe that the triangle 3 will cover the point 5. And this indicates that it's not appropriate. So that's what we observe. Point 5 and point 2 are included. So we have to we need to find out another way to form the triangulation. What we do is like, if we think that is not appropriate, we will try to remove the 2 line that we formed in the second step by connecting the point 6 to the all the parameter to all the points in the parameter, and instead we will try to connect 7 to the point to all the points around the parameter, which will include point 7. So we have 7 to 2 to 3 to 4 to 5 and to 6. And then there will be we will have 1, 2, 3, 4, and 5 triangles, and we still need to check whether the circle formed by the 5 triangles will include any other points. If you go to check the to draw the circle by yourself, and eventually gonna find that it does not include any points in the include any other points you measured. So this means that this kind of triangulation is appropriate and a good strategy for you to form the triangles. So with that, we have finished the triangulation, and we the next thing we need to do is we have to identify the contour plot to show the contour lines with the same elevations. This will be the same example, assuming that we know the elevations of all the points. We have for the point 1, we know the elevation is 11, point 2 is 6, 3 is 10, 4 is 12, 5 is 10, and 6 is 8, 7 is 9. So that's the elevation we measured. Also, we have completed the triangulation. So it should be work as the triangulation should looks like this one. And now, to draw the contour line, we have to find out the location with the same elevations. For the line from 1 to 6, from 1 to 6, the elevation changes from 8 to 11. So it means that on this line, there must be 2 points with the elevation of 9 and the elevation of 10. And similarly, for this line, for the line from 8 to from 2 to 6, the elevation is changing from 6 to 8. So there must be 1 point with the elevation of 7. And similarly for the other lines, here you have 7 and 8, 7 and 8, and here you have 7, 8, and 9. And what you need to do, you at this step, you just need to connect all the points with the same elevation. Here you have 7, 8, 9, 10. And now connect all the points with the same elevation. So you have 7, you have the contour line for the elevation of 7. You have the contour line for the elevation of 8. And also you can find out the contour line for the elevation of 9. And similarly for the contour line of the elevation of 10. So this is how you're gonna draw the contour plot. With that, you can find out the contour lines for 7. For 7, 8, 9, and 10, and 11, and 12, if you have those values. So this is the way for you to get the contour line and to draw the topography map. So with that, there will be the whole process for you to complete the topography mapping. Now there's an issue about the run triangulation. If you have the wrong triangulation, as what we showed previously, if we have this type of the triangulation, it will cause some issue about the drawing of the contour, lines. If we do that way, you will find that there's a very strange point where you will have the elevation of 0.9. The contour line is not quite smooth. It's a zigzag a lot, and this one is not reasonable in reality, and which indicates that the contour line is not right. Or sometimes you will even observe the contour lines are intersected with each other, and that should not happen because for one point, it should not have 2 different elevations. There is only one elevation, so all the contour lines should not intersect with each other. So that's the potential issue about the wrong triangulation. And now I know that the whole process would be very difficult, very complicated. It's very hard for you to do the topography mapping by your hand. So what you can do is like you can utilize some computing softwares to generate the triangulation of a lot of points and also to form the contour, the topographic mapping automatically. So here I'm going to give you an example. So assuming that we have a set of the points, more than 10 points, we know the locations, the X and the Y coordinates. We also measure their elevation. Then we can try to use the MATLAB code to create the topographic map. Generally, we can use MATLAB to first import the data and then use the function of the Denali to create the triangulation and apply the triplot to draw the triangulation. And after that, we're going to have the some contour plot to get the topography map. And this would be the result as what we can generate from the Excel or from the MATLAB code. From now on, you can actually follow the instruction I'm going to show you in the MATLAB code to create the topography map by yourself. I'm going to share my other computer, which can tell you how to do the how to use the code I shared with you on Avenue to Learn. Okay. Okay. So you have received two files. One's the data top file, which will show you the result, the data that you measured. The column A is the X location, column B is the Y location, and the column C is the elevation. And you also have another file, which is called the topography. And double click that file, open it in the MATLAB. It will give you a set of the code. So here will be several steps for you to read through the code. The first part is reading the data from the Excel file. So we have the function to read the data directly from the Excel file. So the data is stored in this code as the data. And now we have the second part about drawing the collected points. So I'm trying to comment the other part so that you can know what happens. You're going to draw the collected all the collected points in the two-dimensional space. So with that, click run. So here's the play button. Click run. You draw all the points in the two-dimensional space, x-axis and y-axis, and those would be the points that you actually drew. We have 11 points. Totally, we have 11 points we measured. And the next step we need to do is trying to apply the Delaunay triangulation. So they're going to try to generate the parameters of all the interior points, and then try to start with searching the interior points and form the triangles one by one until finish the generation of all the triangles. Totally, we're going to have 2 times n minus 2 minus k number of the triangles. So I'm going to show you the effect of the triangulation. So you have drawn all these points, and with the triangulation, you get all these triangles. And if you have time, you can go back to double check the graph to see how many whether the circles will include any other points. So that's the third step about the triangulation. Here we have the function of the Delaunay, which is the embedded function from MATLAB. It can help you to find out the triangles automatically. And you just need to use the triplot to draw all the triangles in the figure. And the last step is the generation about the topographic map. So what you need to do once you here we will have the grid, the mesh grid figure, and we find out the topography with all find out the contour lines with the same elevations from the triangulation that we generated. So what do we do? You do that as a rounded simulation, and with that we have the first figure to show you where the point is. Second figure shows the triangulation, and the third figure shows you the topography map. And you can see that the elevations at this point would be very high, and those contour lines are very close to each other. Means that the slope there is very high, but for those regions it's very small. I mean they are far away to each other. Means that the slope is smooth. So that's the way for you to use the MATLAB code to draw the topography. I wrote this code in the general format. So as long as you input your data to the data topping file, and write them in the same format. The X as the column A as the X coordination, column B as the Y coordination, and column C as the elevation. Then you can run this code and the topographic map will be generated automatically. Okay, so that's the code I'm going to share with you. We have several minutes left, and I want to see whether there's any questions from you. Okay. So let me see the question. There's a question. So for the code implementation of the code, you don't need to write the code by yourself. I have already created all the code, and what you need to do is I'm sorry. Can you see my previous screen? This screen. It looks like I shared the screen, but I did not see it in the other computer. Can you see the screen? Okay. Okay. So just give you a quick hint about the running the code, and make sure that you type the right format in the Excel file. And the okay, the next thing is about the midterm exam next week. So for the midterm exam, we're going to cover the lecture, cover the topics about the angle and the direction, the traverse and traverse computation, and which will be the let me just see the notes, which will be the note note 7 to note 7 to note 11. If you check the note, not the video, check the note in the in Avenue to Learn. There'll be note 7 to note 11. We have 5 course notes to include, and for the format of the midterm exam will be exactly the same to the first one. The time is next Monday from 12:30 to 2:30, and we have 3 questions designed for the midterm exam. But those will be some large questions. You need to finish all the questions before 2:30, and also save several minutes for you to upload your answer sheet. And again the homework assignment and the examples in the course note will be very useful for you to prepare the midterm exam. Also, you don't need to prepare or go through the area computation. it will not be included in the midterm exam. Okay, any other questions? Okay, if you don't have any questions, I guess that will be all for the lecture today. And just feel free to send me email if you have any concerns about the exams and the homework assignment. I have extended the deadline of the homework 5 or homework 6 to Saturday. Please submit your homework assignment on time. In that sense, I can upload the solution for you to prepare for the exam. So I guess that will be all. If they don't have any questions, I will close the meeting today. Thank you very much for your time, and I'm gonna see you next Monday in the exam. Okay, enjoy your rest of the week. Bye.